Imagine training an AI to master a video game. You want it to ace the final level, but how do you know when it's truly ready? Is it just lucky, or has it truly learned the rules? This is the crux of a critical problem in AI research, testing whether an AI's strategy, its policy, is any good. Today, we're diving into a groundbreaking method that solves this puzzle, making AI evaluation faster, smarter, and more reliable. Let's start with the basics. An AI learning to play a game operates in a Markov Decision Process, MDP, a mathematical framework where the AI observes the game's state, like a level layout, takes an action, jump, shoot, or hide, and receives a reward, points, health, or a game over. The goal? Find the optimal policy, a strategy that maximizes cumulative rewards over time. But here's the challenge. How do you test if a policy is good without running endless trials? Traditional methods either take forever or risk missing the mark. That's where this study shines. Researchers tackled the problem in a fixed confidence setting, essentially saying, I want to be 99% sure this policy works, but I don't want to waste time on unnecessary tests. The hurdle. The math behind policy testing often hits roadblocks like non-convex constraints, complicated obstacles that make optimization feel like navigating a maze with invisible walls. Here's where the breakthrough happens. Instead of fighting the maze head-on, the team reversed the MDP, like flipping the game board so the AI's role and the environment's rules swap places. This transformed the problem into one with convex constraints, easier to handle, but a tricky non-convex objective, still tough but manageable. To solve this, they used policy gradient methods, a technique that gently nudges the AI toward better decisions, like a coach giving real-time feedback. The result? An algorithm called PTST that's statistically optimal, uses the fewest samples possible, and computationally efficient, no endless calculations. In tests, PTST outperformed existing methods, acting like a shortcut through the maze instead of getting lost in dead ends. Let's unpack the math. The key innovation was leveraging callback labeler, KL, divergence, a difference meter for probability distributions. Imagine two strategies, one the AI currently uses and one it's trying to optimize. KL divergence measures how much these strategies differ, guiding the AI to refine its approach. But here's the twist. The researchers paired this with convex optimization, a method that ensures the AI stays within safe boundaries while searching for the best solution. Why does this matter? Efficient policy testing is a bottleneck in real-world AI, from self-driving cars avoiding accidents to medical systems diagnosing diseases. This work isn't just theoretical, it's a practical leap forward. By making AI evaluation faster and smarter, we're paving the way for systems that learn better, faster, and with fewer resources. Think of it like giving AI a smarter GPS. In healthcare, it could mean AI that diagnoses diseases without overstepping ethical boundaries. For robotics, it's a robot surgeon avoiding risky moves. Even your phone's assistant could stop wasting time on irrelevant suggestions and actually get what you need. So next time you see an AI acing a game or optimizing a complex system, remember, behind the scenes, researchers are solving puzzles like these to make it all possible. Thanks for watching, stay curious, and let's keep pushing the boundaries of what AI can do.